For the next speaker of today's is Erich Poppitz from University of Toronto, and we'll be talking about sharpening and copying in the semiclassical diagram. So,
thank you very much all for coming, and thanks the organizer for inviting me to this very stimulating workshop. I'm losing my voice. I hope you can hear me. So I will talk about well, that's my title, but the real thing is in the second line. Can we relate various semiclassical confinement mechanisms? And usually people say that if a title has a question mark, the answer is no. I would like to say that not yet. You'll see. Okay. So these are my collaborators over the years, and the title is borrowed from some particular paper. So I start by saying that confinement is, of course, as we all know, a difficult strong coupling problem, non-perturbative on R4. And of course, we know that lattice and also large N will offer a lot of insight. But this talk is pushed in a particular corner in the studies of confinement, and that is confinement with weak coupling using semiclassics. So the first person to realize that confinement can be studied at weak coupling but non-perturbative was Polyakov, who in the 1970s showed that monopole instantons in a continuum language in an SU2 theory spontaneously broken down to a U1. These monopole instantons give rise to an area law of the Wilson loop. They give rise to confining strings, etc. And it wasn't until the 2000s when Unsal, together with Jaffe, Schiffman, and other collaborators realized that the Polyakov mechanism has a very interesting generalization in locally four-dimensional theories. So if you take four-dimensional theories on R3 cross S1 and introduce adjoint fermions with periodic boundary conditions on S1, so the S1 is a spatial, not a time circle, then what happens is that there is a potential for the holonomy, which leads to spontaneous breaking of the gauge group using this language to a maximally abelian subgroup. And there is a number of twisted monopole instantons that appear in that setup. These were not discovered until the 2000s, really. Okay, it's quite interesting developments, both from field theory and string theory. It happened roughly at the same time, and I believe independent. And that I don't know actually. Yeah. Okay. Okay. So in any case, in this case, these twisted monopole instantons play a very similar role to what's happening in the Polyakov mechanism, but it is a locally four-dimensional setup. And there is a whole variety of topological excitations, monopoles, bions, neutral bions, magnetic bions, etc. And this story works in deformed Young mills, which I will define in a little bit in QCD adjoint, and also in super Young mills of any gauge group. So this has been studied quite intensively since then. And in 2022, there was another semiclassically calculable mechanism of confinement, which was it was a very interesting development by Yuya and Mithat, who realized that if you consider R2 cross T2 with the twisted boundary conditions on T2, then you get a semiclassical confinement. The gauge group breaks, SUN breaks to ZN, and the confinement is a sort of a theoretically controlled version of something that Jeff has been, what's the word, promoting since the 1990s, the center vortex confinement. And it also uses insights by González Arroyo and Margarita Garcia Perez and their students who studied the relevant topological excitations. So this is a brief summary of what the semi-classical confinement mechanisms that are currently, so to say, on the market. And the weak coupling is achieved here by having a separation of scales. The separation of scales is that the VEF, which breaks, which facilitates this breaking or this breaking, should be much bigger than the strong coupling scale, like in the standard model. And so this requires that the size of the corresponding space, the S1 or the T2, be much smaller than the inverse strong coupling scale. And of course, this is not the real world. There is no doubt about that. And one, of course, immediately asked whether we should care. And I know many of you have your own answer. My answer is an emphatic no. And obviously, I've been working on that for the last 15 years. And, there is various reasons for that. The first reason really is that it's quite fun. It's quite fun because we can study the non-perturbative dynamics of locally four-dimensional theory in analytically controlled fashion. This is a luxury that we don't often have. Many results have been obtained in this framework. Now, there is also a sort of an overarching hope, which unfortunately is very difficult to push. And the hope is that one can use resurgence theory and resurgence trans theories to sum this semi-classical and perturbative series, and eventually that can continue to strong coupling. Okay, this is a fascinating possibility and fascinating thing to contemplate. Unfortunately, it hits technical roadblocks because doing semi-classical physics beyond leading order turns out to be extremely difficult if you go beyond quantum mechanics of a few degrees of freedom. So, but still, it is a hope, and there's some tantalizing hints that many people here have worked on. Well, here on the first row. Okay, so that's reason number one. And reason number two is that in many cases, in particular deformed Young-Mills and super Young-Mills, there is evidence for continuous connection to the physics on R4. And I will give you one example. Okay, so so this small volume theory remembers features of the physically infinite volume theory, the physically interesting one. And not finally, these studies highlight, in each case, the importance of objects of fraction of topological charges. So this will be a big theme of my talk. And finally, they show the importance of the use of twisted boundary conditions and the relation to recently discussed generalized anomalies. So generalized anomalies, of course, are a big topic, which I'm surprised it hasn't been yet very much discussed in this conference. So Zohar is here, of course. And this business about twisted boundary conditions and generalized anomalies surprisingly has some sort of older precursor. There is this PhD thesis of Tian Warbao from 1984. And for the young people, I can translate the title differently. I can say that it is a study of probing non-perturbative dynamics of gauge theories by coupling to a topological field theory. This is a different way of phrasing the title of this thesis. So if anything else, this PhD thesis is resurging or rising from the ashes because it's really intimately related to stuff we discuss now. Okay, wonderful. So now I want to give you some background. And the background is this. In 2021, with my students, we were studying the mixed anomaly between the zero form symmetries, like discrete chiral symmetry or parity, and one form center symmetry in Young-Mills or super Young-Mills. And we were doing that using the Hamiltonian formalism on T3. So I will just discuss, so this torus will be the main player in what I discussed. So let me just say a few words of what it is. I will discuss SU2 for simplicity. It's just much simpler, okay? Sorry. So we will study the theory on the torus, mostly Young-Mills theory, with a twist of the boundary conditions in the 1-2 plane. So this is the 3 direction, and 1-2 is this plane. So I will twist the boundary condition by what is called a spatial 12 twist, M1,2 equals 1, or M3 equals 1, which is the same thing. Okay. So I have no time to describe what that is. But again, for the younger people in the audience, what this is in modern languages, one turns on a background for the for the 2-form gauge field, gauging the 1-form center symmetry. This background is topological, and the integral of this field, which is usually called B2 over any 1-2 plane, is equal to pi in this case. Okay, so this is has the effect of twisting the boundary. So this is the setup that I will study. And I will not commit to any particular sides, value of the sides of this torus or ratio of the sides or anything. Okay. So this is SU2. And the most important thing in my discussion will be the generator of the center symmetry in the direction of M, so in the third direction. Okay. So this is an operator on Hilbert space. And this operator generates a Z2 symmetry. So it has eigenvalues 0 and 1. And these are known as electric fluxes. So the Hilbert space in this theory splits into so-called electric flux sectors. And one can think, what's the word? Qualitatively about the difference between these two sectors is that the sector of electric flux 1 is obtained by adding a Wilson loop, which is winding once in the direction of the magnetic flux. And the reason this has eigenvalue of t equals 1, so actually the eigenvalue of t is a is a Zn number, but the sorry, it's a nth root of unity, but obviously for SU2 it's 0, 1. So the reason why this has eigenvalue 1 is that this T3 generator, when it acts on the Wilson loop, it gets gives a minus sign, and this is the reason for this terminology. Okay, so very well. So the way the anomaly appears in this setup is the following. For theta equal pi, what one finds is that for all energy eigenstates at any size torus, there is a double degeneracy. The degeneracy is between the energy eigenstates of the Hamiltonian with electric flux 1 and electric flux 0. And this is true no matter what the size of the torus is. So it's an exact degeneracy at finite volume, which is something not very common in quantum field theory. And this is because of the anomaly. If one studies the representation of these operators of parity and center symmetry in the direction of the 't flux in the third direction, one finds that the algebra is what you expect, but there is a minus sign which occurs because of the insertion of these twisted boundary conditions in the 1-3 direction, in the 1-2 direction. So we have these two symmetries which commute with the Hamiltonian, but they obey this Pauli matrix algebra. So this means that all states are doubly degenerate. Okay, so this is background, and a similar thing calls for super Young-Mills, where you replace the parity with chiral symmetry. Okay, so this degeneracy at theta equal pi can be subjected to dynamical checks. And of course, we cannot solve Young-Mills theory on an arbitrary size torus, but we can study it in various limits. And in particular, one limit which can be studied is the limit of the femto universe, where all three directions are small. This notion of the femto universe was introduced by Bjorken in the late 70s for the purposes of taming the infrared divergences of QCD. Then Lüscher studied the spectrum of the femto universe without twists. And then Van Baal was the first one to start studying with a twist, and many people have done that later. So, and of course, this is actually very similar to what Penizaki and Unsal did, because what they did is they took the direction, which is the third direction, to be very large. And this allowed them to study confinement in the big two directions. So this is the new and interesting insight. So we can dynamically check this degeneracy by realizing that on this torus with these twisted boundary conditions, there are only two states which have energy less than L inverse. And one state is, both of these states have classically zero energy. One of them is when the gauge field is exactly zero. And the other is something that looks locally like a gauge transformation thereof. So this T3 is the representation of this generator in the Hilbert space. But globally, this is not a gauge transformation. So there are these two discrete states. I will call them 0 and 1. Again, they're not gauge equivalent. They're distinguished by the different expectation value of the Wilson loop in the third direction. So this has Wilson loop, trace of the Wilson loop equals 1. This has -1. So we have two states of lowest energy, which are related by this center symmetry transformation. And we can form from these two states linear combinations, which are eigenstates of T3, eigenstates with eigenvalue 1 and eigenstates with eigenvalue -1. And by the way, these states were used by Witten to study the Witten index in a twisted box back then. So then what one realizes is that these two states, 0 and 1, get mixed by instantons of topological charge 1/2. And this was first realized by 't Hooft in a pretty old paper from 1979, and then very carefully studied by von Baal. And so these non-perturbative effects, the Q equals 1/2 instantons, lead to splitting of the energy levels between these two electric flux sectors. And this splitting can be calculated in the dilute gas approximation if one assumes that there exist these objects of topological charge 1/2, which are localized in time. And of course, they have some profile on the torus. And this is really all one needs to know. These solutions are not known explicitly. They have been found numerically by Gonzalez, Arroyo, and Perez. And a leading order dilute instanton gas, calling this a calculation is a little bit too strong because nobody really knows the coefficients. The coefficients hides our ignorance the coefficients hides our ignorance about the nature of these solutions, about their multiplicity, etc. So this is stuff we don't know. But the formula is very easy to derive, which I'm not doing here due to lack of time. But what's important is that there is this coefficient, which is 1/2 the BPST instanton action. And this is simply because you expect that the minimum action configurations are self-dual or anti-self-dual. And so they have actions related to the topological charge. Yeah. But this was perturbative. Yeah, perturbative. To all orders in perturbation theory, they remain degenerate because in order to mix them, you require an insertion of the twist in the time direction. And the insertion of the no, not at all. They're degenerate always at any theta. At theta equal pi, they remain degenerate too, even non-perturbatively because of the anomaly, but at other thetas, they are okay. So this expression, of course, can also be written for SUN. I just didn't bother with it. For example, in US paper, it's in there. And the point is that what this shows is that at theta equal pi, these two states are exactly degenerate. You can check that if theta equal pi for E3 equals 0 because of the properties of cosine is the same thing. So this formula, of course, bears close resemblance to a formula that was written by Witten in the large N limit for the theta dependence of Yang-Mills theory. And it was written using a large N argument. Here it appears in semiclassics, in leading order semiclassics, in this small box. It has an interesting history in the sense that in the thesis of von Baal in 1984, what appears is not the formula, but the plot. So he must have known the formula in order to draw the plot. The plot appears. It is referred to as being due to 't Hooft, but it's not published anywhere. And then in a paper of von Baal in 1999, the actual formula appears. Okay, it's a kind of an interesting history. So in any case, so this is the leading order semiclassical story in the femto universe, and also in this Tanizaki-Unsal setup from last year. So what caught my attention, our attention, is that the similar formula is known to occur in a very seemingly different setup. So we have this deformed Yang-Mills theory, which is the first sort of semiclassical setup that I discussed. So we consider R3 cross S1 on a small circle. And I don't know to what extent people are familiar with deformed Yang-Mills, but one way of defining it is to say that you consider 4D Yang-Mills with one direction compactified, and you introduce a potential, which is a double trace deformation. And this potential with some coefficient C requires, this is the trace of the Wilson loop in the compact direction. It really requires, minimizing this energy requires that the trace of the Wilson loop be 0. So this means that you sit at the center symmetric points. It is possible to UV complete this because people often complain that this is a non-local deformation, et cetera, et cetera. But for now, I can just use this. So in deformed Yang-Mills, this formula, identical formula obtains for the difference between the vacuum energy between some two extrema of the potential of deformed Yang-Mills. And in this case, there is no Hooft flux to speak of. And also there is no obvious relation between this index K and electric fluxes. So, what I wanted to understand is why this formulae, and both these formulae agree with what we expect from the theta dependence of the pure Yang-Mills theory vacuum energy on R4. So, so these semiclassical limits capture some important differences. So what I set up to understand is several things. The first thing I want to understand is why these formulae are so similar. And I think I know the answer to that question. The thing that I don't know is what is the relation between the corresponding topological objects of charge 1, 2, of charge 1/2, or 1 over n in the case of SU. So the topological objects on R3 plus S1 are the best understood objects of fractional topological charge currently. They're very well understood from field theory. They're very well understood from deep brain physics. There is expressions for them. The relations of these objects to the BPST instanton are also quite understood. So really what happens is that the BPST instanton fractionalizes in this fractional charge object. So it's quite an interesting development from the 1990s, which is what facilitated this. These objects are, on the other hand, in a very poor poor situation of our understanding. We don't have a good handle on what they are, what their modular space is, how many there are, etc. Okay, it's something that it would be nice to understand. So so what I said now is these transparencies. So basically, what I want to see is, can we relate the semi-classical confinement mechanisms in these two semi-classical units? In order to address this question, I will do a slight reformulation of the Difford-Yang-Mills theory, hoping qualitatively that it makes not a big difference. So what I will consider is the theory, what I call Difford-Yang-Mills with flux, or any other QC, for example, it could be QCD adjoint with flux. So I will consider the S1 direction to always be small, and I will consider a T2 with a twist of the boundary conditions, and the size of this T2 can vary continuously. If the T2 is tiny, 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 so all the three directions are of order L, are small, we obtain the femto universe, and we can also relate this to the Tanizaki-Gonsalves construction. On the other hand, if we take the T2 to be very, very large, much bigger than the size much bigger than the confining scale, and we can eventually take it to infinity, we expect that it doesn't matter, and one should recover the physics on R3. So this is the setup I want to consider. And just to remind you that in the two limits, in the limit when the T3 is small, in the limit of the femto universe, we have these two ground states, which are Witten's zero energy ground states with differing values, so related by center symmetry, as shown here. In the case of Difford-Yang-Mills with twist, there is a background which was proposed by Gonzalez, Arroyo, Perez, and Okava in 2013, and they threw it out. They threw it out because they were afraid of a tachyonic instability. But then Unsal came in 2020, realized that the tachyonic instability is not very not important. It's pretty far in field space if you have also expectation value for the holonon. So what this background does is it's a background which obeys the boundary conditions, the twisted boundary conditions, but it obeys them because of this term, and it's an abelian background. So this background is in the third direction of the gauge loop. This background has a magnetic flux associated with this. So it has a magnetic flux in the 1-2 plane, which is L1, L2. So this is why it obeys the boundary conditions. This term ensures that this potential is minimized. And it has the correct limit when L1 and L2 goes to infinity. So you can form from these classical backgrounds two quantum states. I call them A plus and A minus, and they're related by center symmetry. Again, in this background, the trace of W3 of the Wilson loop vanishes, but the trace of the field strength with W3 doesn't vanish. So this background have opposite values of some gauge invariant which transforms under center symmetry. So the symmetry realization is the same. And so what you need to, really the only thing you need to assume to reproduce this cosine formulae is that there exists an object which facilitates tunneling between 0 and 1. And again, these objects require an insertion of T3 in the partition functions, which makes the topological charge 1/2. So such objects would exist. So this is really what's responsible for having these two expressions for the vacuum energy identical. Identical symmetry realization, even though the backgrounds are different. And yeah. Oh, not at all. Oh, if who is big? No, but this okay, the S1 I always keep small. Okay. Confined phase. Yeah, confined, yeah, absolutely. Yeah. Center symmetry is preserved. Yeah. Yeah, absolutely. So I want to make it's either because of that, or I can UV complete it using massive hadron fermions, which I will talk about a little bit. There is no there is no transition breaking the center symmetry. Yes. So I just want to say that in these papers we spent quite a bit of time. This is just a technical remark, so you can ignore it. But it is very important to understand so if you're interested in doing calculations with on theories which have some twists of the boundary conditions, it's very important to choose the right gauge for the twist matrices. And depending on the purpose or your purpose, some choice of gauge may be better than other. For example, a gauge where the transition functions are abelian is very appropriate for doing dynamical calculations in this background. A gauge where the transition functions are constant is very important for this background. And it's also extremely nice to define the symmetry operators. This is because the parity operator involves an operator that shifts the theta angle by 2 pi at theta equal pi. And defining it in this gauge is much more favorable than defining it in this gauge. So in this paper, we studied that in great detail. And we showed that this relation, of course, holds also for this background. So this is just a technical remark. But what? Sorry? Oh, at theta equal pi, yes. No, not at all. No, no, because for general theta, they get split by instantons. Absolutely. Temperature is even the wrong language here. Yeah, absolutely. Yes, absolutely. So essentially, my message is this, that the reason why these two formulae look the same is that they have identical. So these are, of course, semi-classically derived formulae. They're semi-classical vacua. The symmetry realization in these two vacua is identical. And the only other thing one needs to obtain this formulae is to assume the existence of some localized objects that carry topological charge 1, 2, 1/2 in the SU2 case, which facilitate the tunneling between these two vectors. Okay? And that explains that. So this is a satisfying result. What is less satisfying and not understood, and I don't understand it yet, is the following. We understand the monopole instantons on the Coulomb branch in the infinite limit of R3. So as I said, we understand them very well. When we compactify the theory with a tooth twist on T2, the nature of these objects is not very well understood. And I think that this is a part which can be done analytically, but it's on my wish list. I'm beginning to talk about my wish list and confusions from now on. There are going to be some more results, but it would be nice to understand this. And if we understand what these objects are, maybe built out somehow of this monopole instantons, then we can continue reducing the size of the torus, eventually reducing to the femto universe, and maybe find a relation between these objects and these objects. And then, of course, we can relate these objects to the center vortices that Yuya and Mithat found to cause confinement, sort of putting Jeff Greenside's mechanism on a sort of an analytically tractable footing. Which no, you're. Yeah. Okay, say it again. Say it again. Mm-hmm. Yes. Yeah. Yes. Absolutely. Yeah. Okay, this is look, this is semantics. Yeah, this is semantics. Okay, the actual field configuration has topological charge one. Yeah. You could, sure. Absolutely, yes. Yeah, absolutely. Yeah. I did not present the calculation. I'm sorry. Okay, yeah. You can say that. Yes, absolutely. So this is part of the wish list, okay? And of course, I don't even know how to do this. But essentially, what I want to relate is this monopole instantons to the center vortices. And maybe that's possible to do analytically. I don't know. Maybe it's not. This part is possible to do analytically. I'm pretty sure. I just haven't. Yeah. It says you too, but it could be this. But it could be anything. Yeah. Of course. Yeah. So this is the goal, okay? This is a wish list, okay? I don't know the answer to this. I told you that I'm not gonna, my talk has a question mark, okay? But what I will do is something simpler, but still it required quite a bit of computation. And this is the following. I will study the vacua starting from a large T2, reducing its size. And the way I will do this, I will UV complete before Yang-Mills theory. So this potential can be thought of as due to massive adjoint fermions. Their mass is about 1/L. I can also study QCD adjoint. This is a theory with massive massless adjoints. And on R3 cross S1, this potential is a version of what is usually called the GPY potential, except it has opposite sign because of the fermions. And it guarantees the preservation of center symmetry. So I want to study that on the T2 with twisted boundary conditions. So I will start with this background, but I will allow this holonomy to be not center symmetric, but to be anything. And I will study how the vacuum energy of the theory changes as one changes the ratio of the size of the small s1 and the size of the torus. So this epsilon is the square of the ratio of the size of the torus. And I call this the GPY potential for this modulus. I will spare you all the details, but the main message from here, first of all, is that this background, which was proposed by Unsal and Gonzalez, Arroyo, and others, is consistent at sufficiently large L1 and L2. What's interesting here is that you can look at these curves. So epsilon 0.01, this means that the ratio of the size is 10. And you cannot tell apart the potential in the infinite volume limit from the potential in the finite volume when the ratio of the size is 10. Only for these values you can tell them apart. But there are two messages. The first message is that this potential is consistent in the UV completion of the four Yang-Mills theory. It's also consistent in our QCD adjoint. But also this center preserving minimum remains one up until values of the size, which are of the same order. This suggests that the validity of the two semi-classical descriptions may actually overlap. So it gives us hope that one may be able to study the transition from one to the other. I don't know, okay? So I skipped you all details here. It's as opposed to the GPY potential, where you can actually write an expression, this requires numerics. What you do is you calculate the spectrum in this flux background, and then you sum all the modes, sum their energies, and you have to make it into a convergent sum, and then you calculate it numerically. So it was quite challenging. Obviously, I didn't do that, but it's what it is. So this gives me hope that one can study the transition semi-class. I don't know the answer. How am I doing on time? I'm pretty close, actually. Okay. So now I start with my confusions. Because we had all the formulae, we could also do this for super Yang-Mills. Okay. So for super Yang-Mills, what you find is that the center symmetric point is actually a maximum of this potential. Okay. And of course, this is not unexpected because this background carries non-zero energy. So it's not a supersymmetric background. Okay. So so a flat direction, which you expect in supersymmetry, is only found in the limit when epsilon goes to 0. Of course, in the limit when epsilon goes to 0, there is no GPY potential because this thing disappears, the flux disappears. But for any finite size of the torus, this is not a supersymmetric point. And as a matter of fact, Witten showed in his paper on the Witten index that the only classical supersymmetric states on a torus with twisted boundary conditions in the 1-2 plane are these two states, which are contribute to the Witten index. And these two states have a value of the trace of the Wilson loop, which is plus or minus 2 or plus or minus 1. So they correspond to classically to center symmetry broken states. So to me, this is very disconcerting because it appears that I can do semi-classics only in the infinite size T2 and not at any finite size. And it is disconcerting because you expect that this T2 could be infinite size. Normally, the way we do semi-classics is we go on a flat direction, right? We choose a value for the holonomy. Then we study what the non-perturbative objects are. We calculate the potential, the superpotential in any mechanism you want. And then you find miraculously that in super Yang-Mills, the non-perturbative potential puts you on the center symmetric point. So there's a non-perturbative potential that puts you on the center symmetric point on R3 × S1. And on T2, even this the T2 with twisted boundary condition is flux size. I don't know how to do that because the classical background does not allow you to have center symmetric holonomy. It pins the classical vacuum at A = 0. So I would really like to understand this better. And this I have kind of an ode to this because super Yang-Mills offers on R3 × S1 offers the best understood semi-classics. Coefficients can be calculated. We understand determinants because there is only some one loop thing. There is a most detailed semi-classical understanding of confining strings, domain walls, anomalies on R3 × S1. And these are just my collaborators on this subject, and they have also written separate papers. So I wonder if there is a way to salvage semi-classics at large T2 with twisted boundary conditions. And there's experts here on Seiberg-Witten theory. These boundary conditions are supersymmetric. I wonder if there should be a similar issue there that should be understood. So it's a confusion. Another confusion refers to confinement in super Yang-Mills with other gauge groups. So if you study any gauge group on the circle, the confinement is due to monopole instantons, R + 1 of them, which have these topological charges. C2 is the dual Coxeter number. I guess that's what it's called. Yes. Now, so this is the topological charges of the monopole instantons that cause confinement for any super Yang-Mills gauge group on a circle. On the other hand, two twists in SUN do not produce some charges like that. Just reduce charges 1/2, 1/3, 1/4. These are the orders of the center. So is there any relation? In this case, in the case of SUN, we expect a relation. In this case, it's an interesting question, which I would like to know the answer to. And finally, there are more questions regarding super Yang-Mills with twists in semi-classics. Mohammed Amber and I did a calculation of the Guy-Gino condensate on a T4 with a twist. And there is some factor of 2 that we don't understand. There is arguments that result should be exact, but there is some nagging factor. And I will talk about that at Suzy at 50. I will not discuss that here. So this is a page of confusions that I would like answered. And on the less confusing side, to conclude with that, we argued that the reason why these semi-classical formulae for the theta dependence of the vacuum energy are identical in the various limits, that also works for SUN, are essentially symmetry realization and the existence of tunneling of topological charge 1/2 or 1/n. And I think it should be possible to relate these self-dual configurations of charge 1/n in the various regimes. Regimes where different semi-classics overlap exists. There are also numerical studies earlier using twists, various twists and size limits, and likely future one will be needed. And finally, there is this wish list to understand better these fractional solutions on the torus. So this is my story. Yeah. Mhm. It's, it's possible. But that doesn't make sense because this could be Hubble size. How can it affect the physics? You know, it's well, sphere breaks supersymmetry. These are non-supersymmetric boundary conditions. So on a sphere, you have to turn on some other, but I think Thomas knows what you need to put on the sphere. Yeah, yeah, okay. So it breaks supersymmetry. Here, at least the boundary conditions are supersymmetric because the twists are the same for bosons and particles. No, this is the classical statement. The classical statement is not true quantum mechanically because when there is no abelianization, the theory belongs to strong coupling. You cannot trust this classical thing. No? The reason we study, the reason at the small circle size, so where was this? Yeah. So the reason at the small circle size, you trust to some extent the classical reasoning is that you have abelianization. You sit at this point and the gauge group is broken and the circle is small, is broken at the high scale. If you sit here or here, the T2 is huge. The KK modes come down and the coupling becomes strong. So you cannot address it. I have no doubt that the supersymmetric ground state will evolve continuously. But what I am seeing is that the description of this state, the derivation of this state does not seem to allow for me to use the semi-classical methods continuous. So some insight is required, which is, that's why I'm asking the question, because there are smart people here, you know. So. Oh dear. Mm-hmm. Mm-hmm. But I'm not reducing. Okay, okay. Okay. But this is a very different limit than what I'm considering. No, because I have the S1 always small. I had the S1 small and I varied the T2. So it's a very different limit that you're describing. I want to see how the large T2 and the infinite R2 cross S1 limit are connected, and I don't know how to do it. Mm-hmm. It's a very different limit. Sorry? Sphere? Because, okay. It has,
There's no boundary conditions.
it doesn't have. Okay. It has curvature.
That's
That breaks you.
That breaks
you.
is he broken in arbitrary gravitation? I guess
Yeah,
you need
yeah,
to
yeah,
supergravitate.
Of any particular background breaks supersymmetry.
But could you have like